Hello everyone, this is one of the two videos you should watch before the third session of this week. The idea is that you watch one of the two videos and explain that video to another student so that the other video is explained to you by another student. The details of this I discussed last lecture and can also be found on Brightspace. So I hope you're watching this and as the only video you're watching before the next lecture. Having said that, let's go to the video. So, welcome to this video of the course Algorithms and Data Structures about 2-4 trees. So, last lecture we have seen AVL trees, and AVL trees we saw that they have operations which take O log n. And this is guaranteed by the fact that the search tree stays balanced by the AVL balance condition, so that the heights of the children of each node differ by at most 1. So in this video, we're going to see one of the other trees that does the same thing, just a bit differently, namely the 2-4 trees. But before I talk more about 2-4 trees, I have to talk about multi-way search trees, because 2-4 trees are multi-way search trees with an extra condition. So multi-way search trees are trees with these three properties. And what these basically mean are, well, each node has at least two children. That makes sense. Each internal node with d children have an ordered list of an amount of keys, which is 1 less. So for example, the root node has 3 children, so it has an ordered list of 2 keys. And this node has 5 children, so it has an ordered list of 4 keys. And lastly, all the subtrees of a node are between these values. So the first subtree of this node should all be under 2. So the 1 is under 2. The second subtree should all be between 2 and 12. The third between 12 and 20. You can see this is true. The fourth between 20 and 40. This is also true. And the fifth above 40. You can also see that in this root node, the first subtree, all values are below 50. In the second subtree, all values are between 50 and 60. And in the third subtree, all values are above 60. So multi-way search is a lot like searching in a binary search tree. For example, if you search for 80, then we look if it's where it falls in this ordered list, and we see, well, it's above 60, so we go here, and we see it's above 70, so we go here, and now it's between 75 and 85, so we're going here, and that means we have found 80. So the complexity of multi-way search, again, like binary search trees, depends on the height. So if the height is somewhere with O log n, then this is our complexity. But in the worst case, this is actually O n. So this is a balanced multi-way search tree. So here we get a complexity of O log n. And this is an unbalanced multi-way search tree where the complexity clearly is O n. So 2-4 trees are multi-way search trees, but with a size and a depth property. So the size property is that every internal node has at most 4 children. This is why it's called a 2-4 tree. It has 2, 3, or 4 children, because it has to be at least 2 and at most 4. And then it has a depth property. All external nodes have the same depth. So as you can see, all these external nodes have a depth have the same depth. They are in the same layer. And here as well. So how do we put an entry into a 2-4 tree? This is actually really similar to a normal binary search tree. So first we start with searching for where the element needs to go. So say we're inserting 16. We see it's below 40, so we need to go to the first subtree. Then we see it's between 14 and 20, so we go here. Now, of course, we don't put it in this node because that would break the depth property. So we're actually putting it into this list. So then we get a 2-4 tree that looks like this. Now, in this case, that's fine because there's still 3 numbers. So that still is okay by the size property. But if we now add, for example, another number, say 18, then we would have an overflow because we would have 4 numbers here. So that it becomes a 5 node. Now, an overflow we can solve in the following way. So here we see our node that overflows with 4 keys and 5 children. And we're going to actually split this into multiple nodes. So what we're going to do is we're going to say we have one node with K1 and K2 and one node with K4, and the K3 we're gonna put into the node above it. If there is no node above it, we make it the new root, and otherwise we merge it into that node. Now, of course, that node can overflow again, and then we do that recursively until it doesn't overflow anymore, until the top of the tree. So, to look at an example of that, say we need to insert 48 here. We're first going to search. 48 is between 40 and 60, so we're going into this tree. It's between 45 and 49, so we're going into this thing. So we add it here. Now, this node overflows because it has now 5 children, 4 numbers in the node. So we're going to split this. So we're going to put the 44 and the 45 into this node, a 49 into a new node, and we're putting the 48 here. So that this is still between 40 and 48, and this is between 48 and 60. And now we have created an extra node, which is fine for the depth property, but in the process we created another 5 node with 5 children, 4 numbers. So this overflows again. And what we're doing now is, again, we're splitting this. The 10 and 40 go into this node, the 60 goes here, and because it was the root, there's nothing above it, so we create a new root of 48. And as you can see, by doing this, we also created, we made the height 1 more. So this is how you handle insertion into a 2-4 tree. Now, how do you remove an entry from a 2-4 tree? So again, this is similar to the way binary search does this. So what we're going to do is we're going to remove it like binary search and then repair if needed while traversing upwards. So if you remember correctly, say we are removing the 4 here. What we're going to do, because it still has 4 children, so this still needs 3 numbers. What we're going to do is we're taking the maximum number in this left subtree. So we're putting the 3 into the space where the 4 was, and thereby also removing this. So the 3 is the maximum element of this left subtree. And by that, we have removed this element and still have a correct 2-4 tree. Now, it can also happen that when we remove, for example, 11 here, and we're looking for the highest number just below 11, which is 10, and we're putting the 10 here, this node becomes empty. And by that, we have created an underflow. And this also makes the size property not true anymore. Because a node cannot be a one node with 0 numbers. It has to be at least 2. So how do we solve this? So we can solve this in 2 ways, using transfer and fusion. So if we have an adjacent sibling that's a 3 node or a 4 node, so for example in this case we have a 3 node here, what we're going to do is we're going to put the P here, the K1 here, and the K2 here. So we are basically transferring these numbers here, and by that we also need the subtree T2, which is higher than P but lower than K1, should then be here. And then you see it's quite balanced again. So this is how we solve underflow if there's an adjacent 3 or 4 node. If that's not the case, if the only adjacent nodes are 2 nodes, for example here, then we do fusion. So basically we fuse these nodes into one by putting one of the keys of the above node into it, so that it's 2 again, because this T2 should still be lower than P2. So here you can again check that each subtree still is between the correct numbers. T1 is still below P1, T2 is still above P1 but below P2, T3 is still between P2 and K, and T4 is above K. Now, it can happen, of course, that another underflow happens. And then we do this recursively upwards. So, for example, say we remove 11 like the previous case, then what we have is this situation. There is an adjacent 3 or 4 node, namely a 4 node right here. So we're going to transfer this over here. So what will happen is that the 12 goes here and the 10 goes here. And then our subtrees will still be correct. So this would be the result. Now, what if we would again remove the 11, but all the adjacent nodes are 2 nodes? In this case, as we saw before, we need fusion. So what we're going to do is we're going to fuse these 2 nodes. And by that, we're going to place this 10 over here. And again, this becomes a smaller node, and if it underflows again, we should go that to the top. But this is now not the case, so this is the result. Now, as you hopefully saw, the time complexity of all these operations is O log n. And this is similar to AVL trees, because the height of this 2-4 tree is guaranteed to be O log n. You can look for the proof in the book. The split, transfer, and fusion operations take O1 time, and we are moving through the tree only in downwards and upwards direction and not branching off. So we're only having the height of the tree amount of nodes that we do this for. So to end this video, let's talk a bit about why we're using those balanced search trees, the ones you've seen, instead of just simple hash tables, because hash tables have O1 operations, and these search trees we've seen have O log n operations. Why do we actually do that? Well, there are a couple of reasons. So, hash tables do not support fast operations for other things we might want to do, like finding the minimal element and the maximal element. In hash tables, the elements are not sorted in any way. So to find the minimal element, we're gonna need to iterate over each of them. While in these search trees, we can just take the left tree of the left tree of the left tree, etc., traverse it once to the height, and it takes O log n time. And also, hash functions need to be good, otherwise the time is still O(n). And periodic rehashing can be a problem. And in contrast to that, the balanced searches we have seen are all O log n time for the core operations, and also for the operations, for example, looking for minimal or maximal element, or for in-order traversal. So if you look at the sorted map interface, you see that it has a little bit more methods than the core operations we've been talking about. And all those operations take are a bit faster using these search trees. So you can see that very well in this picture. For example, we want the first entry, we can just search and traverse the tree only to the height. So if you want to get an overview, here's a table. So again, for the balanced trees, you see that all these methods are O log n. Well, for hash tables, the get, put, and remove are pretty fast, in expectation at least. But the other methods you might want to use are O(n), so they're a lot slower. If you want to look at even more implementation of sorted maps, they're in the book. You can look at the splay trees in chapter 11.6 or skip lists in chapter 10.4. But these are not part of the lecture material. So, before the next lecture, as you hopefully know from the last lecture or from the instruction on brightspace, pair up with a student, explain the content of this video to your partner so that your partner knows this stuff, and then learn the content from the other video from your partner. Let them explain it to you. Then try to compare the different trees you saw. So you saw a tree, they saw a tree, and compare how they work. And then, if you need to, check in the corresponding book chapters, 11.4 and 11.5, whether you understand everything. After that, you can come to the lecture. So, that was it for this video. I hope to see you in the next lecture. Bye.